Welcome to MOVI-C Cabinet and Decentralized VFDs 201. This is Session 4, Startup, Manual Mode, and Tuning. In this session, we're going to do our second lab. We're going to get our VFD operational so that it can start running the motor. Some people call this commissioning. Commissioning can be very simple or it can be relatively involved, so we're going to look at different aspects of it. As you'll see with a number of our lab sessions, I have to give you some groundwork information that makes the lab more intelligible, so we're going to spend a few minutes talking about issues surrounding commissioning, and then we'll go ahead and do the actual lab. Let's go ahead and get started. We're going to start by talking about motors and MOVI-C. One of the nice things about MOVI-C VFDs is many of them support a wide range of motor types. The exception is, of course, the lower-end entry-level VFDs, the MOVI-Tracks, but the MOVI-Drive technology, system, and modular support a huge range of motor types, and I'm going to show you some examples here. They support your classic asynchronous motors, sometimes called squirrel cage or induction motors. SEW's popular version of this is our DRN motor. But we also support permanent magnet synchronous motors like the SEW Eurodrive CM3C. We support electric cylinders and linear motors. We also support more exotic motors like line start permanent magnet motors and interior permanent magnet motors like the DR2C, which is a relatively new motor from SEW Eurodrive. It has the advantage of being extremely energy efficient, therefore it's popular in applications where energy is at a premium. And also we support many third-party motors, the blue motor here. This is a generic asynchronous motor. It's no problem getting these operating on MOVI-C cabinet VFDs. A closely related topic that we do need to think about is whether or not the motor has an encoder or a resolver which provides speed and possibly position feedback to the VFD. While it is certainly possible to run a motor without feedback, you can get far better results if it's available, and when you're doing positioning, it's usually essential. This picture shows a variety of motor encoders and resolvers. They all attach to the end of the motor shaft in some way. There are many different types of motor encoders, but if you've got one, it's very likely you'll be able to connect it up to a MOVI-C VFD and take advantage of its feedback. Many MOVI-C cabinet VFDs have what's called a multi-type encoder interface, meaning they can work with a wide variety of encoders and resolvers. The MOVI-Drive technology is certainly in this category, and it supports, as you can see, many common encoder and resolver standards like sine, cosine, TTL, HTL, hyperface, SEW RS485, which is sort of like hyperface, RS422, MOVI-Link DDI, and resolvers. People often ask me in my classes, is it possible if I need two encoders, can I connect one to the MOVI-Link DDI and the other to the encoder interface? And I have to reluctantly tell them, no, you can't do that. When you activate the encoder interface, it shuts off MOVI-Link DDI, and when you activate MOVI-Link DDI, it shuts off the encoder interface. So you can only use one at a time. What if you do need two encoders, however? Is there a solution? Of course there is. You put an expansion card in the VFD and add a second encoder interface. We offer a number of expansion cards, and you can see they support similar standards to the built-in encoder interface, but there are a few differences which I've called out in blue so you can notice them. Closely related to encoders is something called an electronic nameplate. An electronic nameplate, which also goes by the name electronic label, is the equivalent of your traditional physical nameplate on the motor. It contains the same information, the electromechanical information, like the motor's voltage, current, frequency, nominal speed, and power factor. The VFD needs this information in order to be commissioned. Now, if you have just a standard physical nameplate, then what you can do is enter that information in when you commission the VFD. On the other hand, if you have an electronic nameplate or an electronic label, the VFD can read it automatically, which speeds up commissioning substantially. Now, electronic nameplates can live in two different places. One is in the encoder. Some encoders include an electronic nameplate, some don't. Hyperface encoders are a common example of those that often do. What will happen is if you plug into the encoder, the VFD will be able to read the nameplate and use it during commissioning. Now there is one little gotcha with electronic nameplates and encoders. If a maintenance person swaps the encoder to a different motor, the nameplate goes with it. If that motor does not match the nameplate, then you've got a mismatch, and that means you could miscommission that motor. So you should always kind of check the information that's coming back from the nameplate just to be sure it looks realistic before you accept it. MOVI-Link DDI motors always include an electronic label, which is essentially the same thing as an electronic nameplate. It's built into the motor itself, so it can't get moved around during maintenance, which is a nice thing, but it provides the same basic information. That's yet another reason to buy a MOVI-Link DDI motor if you have a choice. Now, time for another big idea. Most MOVI-C cabinet VFDs can run the motor in one of two modes, what we call open loop or closed loop. What is this? Open loop simply means you don't have any kind of feedback from an encoder or a resolver. Now, if you're in open loop mode, what the VFD does is it measures the current running through the motor, it does some calculations, and it can kind of estimate what the motor speed is. Open loop speed control obviously is less precise than closed loop, but it can be very good in some motor modes. MOVI-C VFDs support certain control modes that are actually pretty good open loop. Closed loop, though, is better because in closed loop you do have exact information coming back from that feedback device. Now, as a side note, I've said this already, but I'll say it once more. If you're going to do positioning, you almost always need closed loop. Most MOVI-C cabinet VFDs have 4 different motor control modes, and you may wonder, why do we have that many? Well, of course, there are different kinds of motors in different degrees of performance. Let's just summarize the 4 modes very quickly. The first is called VF mode. It's sometimes called volts per hertz mode by some people. It's a very simple mode. It is open loop only. You cannot use feedback even if you have an encoder. If you hook it up, it will just be ignored. It works only with asynchronous motors or induction motors. It provides basic speed control mode. You can run motors in parallel if they're very close in size. This is really just a very bare bones mode. It's good if you're just running an asynchronous motor and you don't care too much about precision, or if you're trying to get a third-party motor working, this is a good place to start. But a much better choice is VFC plus mode. VFC stands for voltage flux control. It can be used either open or closed loop. Obviously, you'll get better results with closed loop, but it does a very nice job even open loop. It works with asynchronous motors only. It gives you very accurate speed. It gives you good torque control, and if you have closed loop available, you can do positioning with it. It's also good for dynamic situations where the motor's starting and stopping, changing speed or direction frequently. The third motor control mode is ELSM, which stands for Encoderless Synchronous Machine. It was introduced by SCW Eurodrive with the MOVI-C portfolio. It is an open loop only mode for permanent magnet synchronous motors, commonly called servo motors. In the past, it was often very difficult to run a servo motor open loop, but ELSM solves that little problem. It gives you good basic speed control and basic torque control. It's only suitable for horizontal applications, and you can only run a single motor. You can't put them in parallel. But if you're using a servo-type motor for a speed control mode, it's an excellent choice because you can save the money and not put an encoder on that motor. And the last mode, which is the very best mode and the preferred mode that you should use if at all possible, is CFC mode, which stands for Current Flux Control. It is a closed-loop only mode, so you must have a feedback device, but it works with all motor types. It gives you very accurate speed control, good torque control, excellent positioning, and it's very good for highly dynamic situations. Many of our field engineers at SCW Eurodrive recommend you use it if possible because using it can solve many problems. So these are the 4 modes available with MOVIDrive technology, MOVIDrive system, and MOVIDrive modular. After we get our motor doing basic operations, we usually have to move on to a second step, which is also part of commissioning. It's called tuning. Now, tuning is widely misunderstood by many people, and the reason is very simple. It can mean two different things depending upon the situation. So let me give you a definition of each type of tuning, and then I will talk about the tuning we're going to perform in the next lab. Now, the first definition means adjusting the VFD's motor settings so it can optimally control a specific motor model. Now, notice I'm showing a generic third-party motor here, and there's a reason for that. When you're using third-party motors, you do need to tune them as part of the commissioning process, and that's because our VFDs don't know a whole lot about their electromechanical properties. So what you do is you enter the motor's nameplate information, and then you enter what's called a measurement cycle. What the VFD will do, it will run a small amount of current through the motor's windings. Sometimes you'll hear this kind of groaning noise from the motor, and the shaft may twitch a little bit. After a while, the VFD will say, okay, I've got the measurement. It'll set some parameters, and at this point, it can optimally control that motor. That is type 1 tuning. Now, with SEW Eurodrive motors, you never have to do this. You never tune them using type 1 tuning, and that is because MOVISUITE already knows all the electromechanical information of all our motors. It therefore never needs to run a measurement cycle. All right, so that's type 1 tuning. Let's move on to the other type. This is the one we're going to do in this lab activity, and this one has nothing to do with the brand of the motor that you're using. Meaning number 2 means adjusting the VFD's control system so it can manage the load quickly and accurately. Now, I'm showing you an application here on the right, which is an excellent illustration of why you have to tune the VFD. You may have seen one of these before. It is a sheet metal winder. It rolls up a gigantic sort of toilet paper roll of sheet metal. As you can guess, there's a lot of mass in that roll. That thing is incredibly heavy. And if you've ever taken a physics class, you know that mass is equivalent to another property of matter called inertia. Inertia is the property of matter that makes it resist changes in its motion. If you try to move something which is not moving and it's got a lot of mass, it's going to be very hard getting it moving. But once it's moving, if you want to stop it, it's very hard to stop it. That is inertia. Now, whenever you have a lot of inertia out there on the load, the VFD could have some trouble controlling it if it doesn't know how much inertia is out there. The VFD therefore needs to know the inertia value in order to control the load properly. So it has to be entered in or measured. You also have to do something else. You also have to tell the VFD what stiffness you want when you're controlling that load. Stiffness is the precision by which you're controlling the load. Are you starting and stopping it on a dime, or does it not matter a whole lot? This is something that every application has its own unique value. When you set it, that is part of the tuning process. So another big idea here, tuning in the sense of meaning number 2 means 1, measuring the load inertia or entering it in, and 2, setting the optimal stiffness. And then finally, when you do this, of course, you've got to confirm that the control system really works as expected. This is one of those art forms of commissioning, and some people are better at it than others, but it's important, especially with challenging applications. Let me talk about something closely related to this kind of tuning, and that is maintaining control of the load. The VFD's control system needs to handle changes quickly and accurately when it's controlling the application and the load that it's attached to. Let me give you an illustration of this. We have a simple conveyor here. The conveyor at this point is empty. It is running at a fixed speed that we have selected. We call that the set point. And the control system is simply trying to maintain the set point. It's trying to maintain a constant speed. The way it does this, it adjusts how much torque the motor is delivering. Now, if the motor is driving an empty conveyor, it's delivering just enough torque to keep everything rolling and nothing more. If I were to graph the torque over a period of time, it would look something like this. It would be a horizontal line at some small value as the conveyor is just moving those rollers. But what happens if we change conditions very suddenly? We drop a box on the conveyor. That adds a load to the conveyor that wasn't there a second ago. Obviously, more torque must go into that conveyor to keep it running at the same speed or it's going to slow down. What the VFD would have to do is detect the change and increase the torque. You're probably looking at this and saying, yeah, right, that never actually works that way in real life. And that is true. This is what we call an ideal response. If the world were perfect, the VFD would do this. But VFDs can't do this, motors can't do this. You can't instantly change from one torque level to another without skipping a beat. What actually happens is something more like this. This is what we call a real response. There's a delay before the VFD even starts changing things, then it takes time to make that change. It probably overcompensates, and so it overshoots the required torque, and then it corrects it, undershoots it, overshoots it again, and eventually settles down to the new level. All right, the VFD is doing this every time something changes. Either you change the set point or you change the load. This comes back to our motor modes. Different motor control modes handle this situation differently, and each one has a characteristic response. VF mode and ELSM, which are both open loop modes, they take a while to handle changes. VFC Plus, on the other hand, it does a better job. You notice it locks onto the new conditions pretty quickly. And CFC mode, as you can see, is excellent. It handles changes very quickly and accurately. Another big idea: in order to do these things well, the control system must know the load inertia and the optimal stiffness to maintain good control over the load and take advantage of what the motor control mode can offer. In other words, you have to tune things. So how do we tune the VFD in the sense of meaning number 2? Well, MOVISUITE can measure the load inertia semi-automatically if you don't know it. That's what you'll be doing in this lab. We're going to measure the inertia of a flywheel attached to our motor. That's not the most exciting application, but it's easy to measure at least. And we're going to set the stiffness to a default value in our first lab, but in a later lab, we're going to use a tool called the scope tool to set the optimal stiffness, which we do visually. In the meanwhile, it's time for our basic commissioning lab, so let's go ahead and dive in and do that. Get out your lab manual or open the file, and please turn to lab number 2. Go ahead and pause the video if you're doing the lab, and when you're done, come back and I'll go through the walkthrough. All right, well, I hope your lab went well and you got your motor commissioned and found it interesting and enjoyable. If you weren't able to do it, or if you'd just like to see how I do it, I'm going to do a walkthrough right now. As you can see, we're right where we were in our last lab. We have lab 1-2 loaded. Our VFD is still connected. We're ready to go and begin our commissioning exercise. So following the instructions, I make sure that my demo unit's DI00 switch is off. That inhibits my drive. That's a smart thing to do because you wouldn't want the motor to accidentally move during commissioning. In a real-world application, that could be very dangerous. So we disable the drive. Now the first thing we need to do is factory reset our VFD. Now actually my VFD has already been factory reset. The way I know that is because it's displaying C4 here, which means that it's been factory reset and it has not been commissioned. But we're going to go through that process anyway because normally that's a really smart thing to do when you do a commissioning. So I double click on the top of the VFD circle. And notice everything is still open from my last lab activity, so let's clean up our screen a bit. I'm going to right-click on one of these tabs, and I'm going to close all the tabs. I'm also going to collapse all my menus, and I'm going to now go to the Device Properties menu, expand it, and then expand the Basic Settings submenu, and open Reset Device Parameters. Now right here, I've got a button called Delivery State. If I click this, it's going to reset my VFD. Unlike some of SEW Eurodrive's earlier B generation products, which took you at your word the minute you clicked it, in the MOVI-C product line, we double check and say, do you really want to do this? And I do, so I'll go ahead and say yes, restore delivery state. And that's it. My VFD has been returned to the factory default condition. I'll click OK. There is only one thing I want to point out. The VFD's name does not get reset when you factory reset it. Notice it's still axis 1. But if you go into the upper corner here, we see a C4, which means the VFD is essentially in a blank condition. So now we're ready to commission it. To commission our VFD, we need to go to our drivetrains menu, expand it, and pick drivetrain DT1. There are actually two drivetrains called DT1 and DT2. We won't use DT2 for anything in this class. I will explain what the second drivetrain is for in a later session, but for now just pick drivetrain DT1. Open its page. Now, my particular motor, which is connected up, has an electronic nameplate. It's a servo motor, and it's got a hyperface encoder in it, which can include an electronic nameplate. There is one here. You can see it's been read right here. I could, of course, just click the button, use electronic nameplate to make a quick and easy commissioning. But what I want to demonstrate here is how you commission a motor that does not include an electronic nameplate. We're going to do this the manual way. So I'm going to click Read Motor Nameplate instead, which will ignore my electronic nameplate. And now I've got to type in my motor's nomenclature right here. Now, to get the nomenclature, you need to look at your motor's physical nameplate. So here's what my motor's nameplate looks like, and I can see the key information here. All that I really need to enter is the motor model and size, whether it has a brake or not, whether it has a temperature sensor, and whether it has an encoder. You can skip things like connector nomenclature and flange nomenclature and gearbox nomenclature. That's unimportant at this point. So we'll just go ahead and type this in. My motor is a CMP 50S. It has a BK brake. It has a PK temperature sensor. And it has an AK0H hyperface encoder. So I'll type those things in and I'll click Apply Drivetrain. And there we go. It's done a basic commissioning already. You can see we have our drivetrain up here, the motor, the encoder, and the control system. Now we haven't selected everything yet, so a few things aren't complete. And we do need to go down first of all and double check that everything's right for our motor. And in fact, it's not because the speed class is wrong. This is a 4,500 RPM motor. So I need to change that. The system voltage is fine. The ventilation's fine, the torque at the motor shaft is fine, so that's all good. My temperature monitoring is okay. It is connected up to my VFD through the motor encoder connector, that is fine. My brake is correct, the way it's controlled is correct. So we're in good shape now. We'll go ahead and click the next button, and that asks us about our encoder, and we're not going to change anything here. All the default settings are just fine, so we click next. And then lastly, we have to pick our motor control mode. Now, since this is a servo motor, the only option available to it is CFC. That's because we have an encoder. ELSM has been disabled because that would work only with encoderless motors. But I do need to change one thing here. I need to change the PWM frequency to a higher frequency. Otherwise, I will hear that and it'll be very painful to my ears. 16 kilohertz is almost inaudible to me. Of course, if you have a dog or cat around, they'll still hear it, so you might want to be aware of that. Just remember this, the higher frequency PWM setting is quieter, but it also makes things run hotter. That is something to consider. All right, we need to do one other thing. I need to set my nominal line voltage. It is not 400 volts because I'm not in Europe where that tends to be the standard. It is 460 here in the United States, so I'll type in 460. And then I'll go ahead and click Transfer Data to Device. And I get a warning here. Do I want to go to a startup state? Beware the drive could move and so forth. Okay, I've inhibited my drive, so that won't happen. So I click Activate Startup, and it chugs away briefly, and there we go. We're all done. Now we've done our basic commissioning, but now we need to go and set a few limits to make sure everything's appropriate, and then we need to do some testing. I'm going to now expand my Functions menu and pick Monitoring Functions submenu, and then open Limit Values. And I notice my motor speed is set unrealistically high, so I need to set this. I'm going to set it to 4,500 RPM, which is the motor's nominal speed. I need to set it for both directions, clockwise and counterclockwise. I also need to pick acceleration and deceleration values, and according to my instructions, it says just set it to double the motor's speed. I'll set it to 9,000 RPM per second. That's just an OK generic value. All right, so that establishes some limits on my motor. Now I need to go ahead and do some basic testing to see if the motor runs. So I'm going to fire up manual mode by going to the More menu, picking the Tools menu here, picking Manual Mode. There's my manual mode tool that's just opened up. Now I need to activate it, so I click Activate Manual Mode. And notice it says the output stage is inhibited because DI00 is off. Okay, it's now time to turn that switch on. So I go to my control box and I flip DI00 on. As you can see, that removes the inhibit, and I can now run my drive. So I'm going to do that by clicking the play button here. And I hear a click as my brake releases, and I'm going to start the motor spinning. And you can see there we go, we're spinning away. You check the other direction. Runs in both directions just fine. Notice I can do a few other things. I have a speed reversal button. I can click this to go back and forth. I can also type in a speed directly, like 3,500 RPM. I can change direction just by putting a minus sign on that. And I can also use the keyboard to control manual mode. If I want to stop my drive, for example, I can hit F4 and it will bring it to a stop. Or of course I can click the stop button here. Manual mode is handy just for testing things out. Looks like our basic commissioning did succeed. Now we need to tune the VFD so that it can control the load properly. Now in my case, I happen to have nothing but a flywheel attached to my motor, which is not a very challenging load, but we can still tune it. Of course, in a real application, it would be much more interesting, but we'll do our best with our flywheel. So we're going to go back to the Drivetrains menu and pick Optimization DT1. This allows us to tune our drive. Tuning, as we've already learned, involves really two steps: measuring the inertia of the load and then setting the stiffness. Now MOVISUITE has a semi-automatic tool for measuring the inertia, which we're going to use to measure our flywheel, and we'll just set the stiffness to a sort of harmless generic value to start. The first thing we need to do is click Determine Load Moment of Inertia to begin that process. And I'm going to click Open Manual Mode. And you may be thinking, why do you do that? Manual mode's already open. Well, yes it is, but I want to change to a different version of manual mode that is used for tuning. Notice when I click this, it changes to what's called Load Cycling Absolute Mode. In this mode, MOVISUITE is going to cycle the motor back and forth, and by doing this, it's going to be able to determine the inertia by measuring the jerk as it changes direction. Now I need to do a few things first to get this set up. I need to go over here and click this gear control, and that will open some extra hidden controls, and I need to reference my drive. If you don't know what that means, don't worry about it. We'll learn more about that later. So I click this, and the brake briefly releases, and the motor is now referenced. I'm going to set my acceleration slider to maximum because when you tune the drive, you want to produce a measurable jerk, and you can do that by setting the acceleration to a fairly high value. I need to set my speed. I'm going to set it to the motor's maximum speed, 4,500 RPM. And I'm going to set position 1 to 0, which it already is, and position 2 to 50 revolutions. What will happen is, as my motor cycles back and forth between 0 and 50 revolutions, it will determine the inertia. So here we go, let's do that. Click play. You can see the motor's going back and forth now. And notice a graph appears over here with bars. Each one of these is an inertia measurement. And all I have to do is wait until the bars stabilize, they're about the same height, and this button turns green, which it already has done. So I've got my inertia value. I'm going to just click End Measurement, Save Value, and I'm going to stop my drive from cycling. And there's my inertia value right there. That's what my flywheel is. I'm going to set my stiffness right here to 1. In fact, it's already set to 1. That's a good starting value. My drive is basically tuned. Okay, pretty simple. My instructions mention one other thing I need to do, and that is to set the zero clearance slider all the way up to 100%. This accommodates backlash if a gearbox is attached. Now in our case we don't have one attached, so by setting it to 0, that says we just have a direct drive motor with no gears. Alright, let's shut down manual mode, so we will deactivate it here. And it says, do you really want to do this? And be careful, things could move. So I think I'm going to turn DI00 off just to be safe here. And then click deactivate manual mode and close it up. Okay, so that's a basic commissioning. Now we're going to do it all over again. And you may say, why? I want to show you a tool that makes commissioning a lot easier. What we've just done is a manual commissioning where we do every single step one by one. You have to know the steps to do. I'm now going to show you a tool that was fairly recently added to MOVISUITE that automates the whole process. So let me close up all my tabs here and collapse my menus, and we're going to kind of start all over. We're going to begin by clicking the Overview page here, and this opens a page that identifies my VFD, and it's got a nifty little button called the Startup Wizard, which is the tool we're about to use. So I'm going to click this, and it says, now there's already a startup here. Do you want to just continue editing that, or do you want to start clean? And I say, let's start fresh. And it says, do you want to restore the delivery state? And I say, yes, go ahead. So it does that. This is basically a factory reset. Okay, that's complete. And now the Startup Wizard window opens up here in the middle. It's a separate window actually. And it says, do we want to start up drivetrain 1? And I say, sure thing. Click Next. What voltage do you have? 460. Enter that in. Click Next. Do I want to use the electronic nameplate? All right, we didn't use it last time. Let's use it this time just so you can see how it works. So I pick electronic nameplate, I click Next. It shows me my motor settings, and I'm going to just quickly eyeball them to confirm they're correct, and they look fine to me. So I'll click Next. And there's my drivetrain with everything set up. I click Next again. It gives me a chance to review my motor details. Notice a lot of things are locked out. That's because it's relying on the settings in the electronic nameplate. So it's only letting me change a few things. For example, I could alter how the sensor's wired up to the VFD, but of course I won't because this is correct. So I click Next again. Gives me a chance to change some of the encoder settings. I'll say nope, just go to Next. I am going to change my pulse width modulation frequency to 16 kilohertz to make my ears happy. That's good. Transfer data to device. Yes, go ahead, activate the startup. Now it's going to let me set my application limits. Remember, I set these to the motor's nominal speed, so I'm going to go in here and do this again. Set it to 4,500 RPM in both directions. I'm going to set my acceleration and deceleration values to 9,000 RPM per second. And I've got an emergency stop value, which I really should set as well, and I should never have this slower than the regular acceleration and deceleration. So I'm going to set this to 9,000 as well. I can leave all the other settings alone, so I'm going to click Next. And these settings don't have to be changed. The defaults are fine, so I'm going to now pick Transfer Changes to Device. And at this stage, I could open manual mode, but I really don't need to. I know my drive works, so I'm going to skip that step. If it's all the same to you, I'm just going to click Next. And it says, do you want a MOVI kit? Well, we haven't learned about MOVI kits yet, so let's just click Continue without one. We'll learn about them later. Don't worry about that. Click Next. And again, we've got to determine the inertia, so we need to tune our drive. Let's do that. I click Determine Load Moment of Inertia, open manual mode, activate it. Got to remove Controller Inhibit. I need to open my extra settings here and scroll down and reference my drive. I also need to set my acceleration slider to maximum. And I need to set my positions between 0 and 50 revolutions and my motor speed 4,500 RPM. There we go. We're now ready to take some measurements. Our bar graph appears. The bars are all about the same height and the button is turned green, so I can click End it and accept the value. I can stop my motor from cycling, deactivate manual mode, and I'm going to remove controller inhibit here and go ahead and do that. Close it up. I do need to set my backlash slider to 100% because we have no gearbox. And that's it. Click Next, and it says, hey, you're done. All right, finish startup. And that is that. That was very quick, wasn't it? That's why the Startup Wizard is nice. In general, you should use the Startup Wizard. That way you won't forget anything. But now you know how to do it either way. So we are done with this lab. We need to do just one final thing. I need to save my lab by clicking the floppy disk button, and that is it. Walkthrough is over. Before we wrap up this lab, I want to give a post-lab comment. In this lab, you set the application limits in order to control what the motor could and couldn't do, and we set it to the motor's nominal speed. But you don't have to do this. In real life, it is perfectly fine to set a lower speed for the application limit. You can do this if the application should never run at the motor's nominal speed. Maybe it would only run safely at a lower speed. In that case, set the application limit to that speed instead, and that will protect your application. So just a handy little tip. And that is now the end of our session. In our next session, we're not going to do a lab. We're going to talk a little bit about what is going on inside the VFD, what goes on under the hood. This is going to make some things that we do in the lab after that make much more sense. See you then.